Hello and welcome to this video about optical phenomena. In this video, we are going to look at total internal reflection and the critical angle. We will look at fiber optic cable, mirages, dispersion, and examples of that in prisms and rainbows, and we'll look at lens aberrations. So let's take a look at what we mean by total internal reflection. And to do this, let's look at this example right here. We have maybe a tank of water that kind of looks like water. And let's say we produce a beam of light right here, and it is passing through this first medium, and then it refracts as it crosses that boundary between the first medium and the air. We could change the angle of that, and we could again see that it refracts when it crosses the boundary between that first medium and the air. And we could continue to change the angle that we are passing this beam through that first medium, and we continue to see refraction, but there will be a point that we reach right here. And at this point, the refracted ray is moving parallel to the boundary, right along that boundary. That is called, this angle here is called the critical angle. It is the angle of incidence at which the refracted ray moves parallel to the boundary, or theta r equals 90 degrees. And remember, we can draw a normal line perpendicular to the boundaries there, and this is the angle that we're measuring right here. That's the critical angle. Any angle of incidence that is greater than this critical angle is not going to allow refraction to occur. Instead, only total internal reflection will occur. In other words, when my angle of incidence is greater than the critical angle, I will get only reflection and I will not get any refraction. Here's an example of someone doing this in a little photograph. It's also important to note that even though this is just showing refraction here, there is some reflection that is occurring in each of these points also. But for total internal reflection to occur and no refraction, we have to have theta I greater than the critical angle. Now, of course, we have a very lovely mathematical relationship for all this. When we're thinking about critical angle, if we know something about the index of refraction for at least one of the media, we can find the index of refraction for the other media. Or if we know the index of refraction for two mediums, we can find the critical angle. And these things are all related by this equation. The sine of the critical angle is equal to the index of refraction for the second medium divided by the index of refraction for the first medium. And this works as long as the index of refraction for the first medium is greater than the index of refraction for the second medium. If we look at this example over here, we have the first medium being glass, the second medium is air, and the index of refraction for the glass would need to be higher than the index of refraction for air in order for this calculation to work. So let's try an example together. Let's calculate the critical angle of light traveling from quartz into air. First, let's write down what we know. When we look on our chart for indices of refraction, we can see that quartz is 1.46, and we know it is going to be the index of refraction of our first medium, n sub I. The index of refraction for our second medium is going to be that for air, which is 1.00. Here's our critical angle equation, and we can simply plug values into this formula. I can do the math right here, 1 divided by 1.46, and I can take then the answer to that and take the inverse sine of it, and I will get 43.2 degrees to be the value of the critical angle. This idea of total internal reflection has a very interesting application, and it has to do with fiber optic cable. You've all heard of fiber optic cable. It essentially consists of several different fibers, and light is guided along a single one of those fibers by multiple internal reflections. So it uses this idea of total internal reflection to guide light over very, very, very long distance with very little light intensity being lost. So fiber optics are very useful in telecommunications. They can carry computer signals much more efficiently than electrical wires. And they're also useful in the medical field. For example, a fiber optic device can be used to view images in maybe kind of inaccessible places. For example, threading a fiber optic tube down the esophagus to look for ulcers in the stomach. Atmospheric refraction of light is another interesting phenomenon that we see because of refraction, and you see that every day, every morning when there's a sunrise and in the evening when there's a sunset. The light that is coming to our atmosphere from the near vacuum of space is going to be bent or refracted because our atmosphere has an index of refraction that is very different from that of near vacuum space. We also see atmospheric refraction of light in the case of mirages. And dense air tends to be, cool air tends to be much denser than warm air. And in places, especially desert places, you can get a change in that cool air versus the warm air in relatively short distances. So we end up seeing a lot of mirages in desert locations. However, they can also occur on the road, as we're going to talk about here in just a moment. But when we have different densities, the indices of refraction in that air are going to be different. And so we are going to get refraction occurring. In this case, the observer is seeing an inverted image of that tree. Here's a photograph of some mirages of trees as well. But when you're driving, a lot of times you'll see something that looks like water on the road. And that's because light rays from the blue sky above are being refracted by the warm air that is next to that dark, hot road, and it looks like water. Another interesting phenomena is dispersion. Dispersion, as a definition, is just the process of separating polychromatic light into its component wavelengths. This sounds like a big fancy term, but it just means many colors. So when we talk about white light, that's polychromatic. And when it enters this prism, it's going to be refracted, but the different wavelengths that make up this white light will refract at different angles. And we know that the blue light, it has a wavelength of 470 nanometers. It is going to bend more than the red light, which has 650 nanometer wavelengths, when it passes through this refracting material. And then it bends again as it exits that material. So we end up seeing this rainbow, or a separating into the various wavelengths of that white light. Another example of dispersion is a rainbow. That's created by the dispersion of light in water droplets. And when we have all of these water droplets in the air, we know that these red wavelengths are going to be refracted less, but on the blue end of the spectrum, they are going to be refracted more. And we end up getting a rainbow that's created because of the differences in refraction for the different wavelengths of light. So if you'll remember talking about spherical mirrors and spherical aberration that occurred with those mirrors, creating kind of blurry or fuzzy images, we have the same phenomenon that occurs with lenses. It's just called lens aberration, or spherical aberration for lenses. One particular type of lens aberration is called chromatic aberration. And remember, we just talked about this chromatic idea. It means colors, different colors. Chromatic aberration occurs due to different wavelengths that are refracting at different angles. Here's a picture that just gives you that idea in your mind. We have different focal points, different places that the images are able to focus depending on the light, the wavelength of light and the color of light that is being refracted. So because the different colors of light focus at different distances behind the lens, we get chromatic aberration. And chromatic aberration for a diverging lens would be the opposite that for a converging lens. So we can reduce chromatic aberration by using a combination of both converging and diverging lenses together, made from different types of glass. Are you ready for some advanced ideas? What's the difference between transparent, translucent, and opaque materials? Are materials that are transparent to visible light also transparent to other wavelengths of light? Use that information to explain why you are not likely to get a sunburn through a window. Also, how's the concept of refraction used by gemologists to identify gemstones? What is the process of gemstone identification? Any other questions you have or any other interesting phenomena that you could come up with and explain using all the things that we've been learning about? I would love to see what you have, and we'll see you in class.